Hi, everybody. My name is Michael Wu. I'm the principal and co-founder of Converge Strategies. We're a consulting firm focused on the intersection of clean energy, resilience, and national security. I'm incredibly proud and excited to partner with Idaho National Laboratory for what I think is going to be a set of really interesting conversations around digital engineering. And again, this webinar is digital engineering, aligning federal government needs with national laboratory capabilities. I just have a couple housekeeping comments before we kick it over and start the agenda. So this webinar is being recorded. Both the comments, video, and chat and questions will all be recorded, just to let you know that and disclose that. Secondly, questions, if you have questions that are being prompted by the programming and some of our really fascinating speakers, there's a question box in your control panel on GoToWebinar, and we ask that you keep any substantive questions in that question box so that we can have visibility on those. And if you have any technical issues, we do have folks who are standing by to try to help with that in the chat box, in the chat function, which will be used to address technical issues. Finally, just a little bit of an overview of what we're going to be doing today. We're going to have a really exciting keynote address on some of the things that are happening within the private sector around digital engineering. We're going to have a panel of representatives from the Department of Energy addressing the ways in which the Department of Energy is considering and applying digital engineering tools for our clean energy future. And then finally, we'll wrap with a panel on addressing how the Department of Defense, another huge user of digital engineering tools, is thinking about and applying those to its mission and strengthen its capabilities. But with that, I'm excited to introduce the director of the Digital Innovation Center of Excellence at Idaho National Laboratory, Chris Ritter.
Thanks, Mike, and welcome to the virtual 2022 National Laboratory Digital Engineering Conference. I am so excited to bring our community of government stakeholders, laboratories, universities, and enterprise partners together for the very first time. Today, we have an action-packed 2 hours together, as Mike mentioned. We've got a keynote from Mo, who's already on the screen here. We've got a panel with senior leaders from the Department of Energy and another panel with senior leaders from the Department of Defense. This event is a virtual preview of sorts of our in-person event, which will be on April 25th and 26th of 2023. But before we get to our speakers, I think it's useful to define what digital engineering, digital twin, and digital thread is. Let's start with digital engineering. So DoD defines digital engineering as an integrated digital approach that uses authoritative sources of system data and models as a continuum across disciplines to support lifecycle activities from concept to disposal. So the best way I like to think about it is this is really combining system engineering with that great computational modeling, technology, and data science goodness. Now, to be honest here, the word digital twin is totally a buzzword, and there is now a plethora of definitions. So for the purposes of this event and the next 2 hours together and the inclusion of as many definitions as we can get, we're going to use a maturity model. So there are lower levels of maturity, ranging from the simplest level 0 digital twin, which is like a 3D model or LiDAR capture, to a level 3, where you start getting that integrated predictive AI, and finally to that level 5 digital twin, where the best way to think about it is like your Tesla driving autonomously down the highway. That's really a level 5 digital twin, and a level 0 is the 3D model, and then everything else is in between. So in the chat, one of my colleagues, Jaron Browning, should be posting one of those maturity models that you can take a look at for your use. And finally, digital thread is that software that's connecting all the data together to enable these digital engineering and digital twin ecosystems. And across the federal enterprise, research is ongoing to build these new digital ecosystems and enable clean energy, security, and defense of our nation. Commercial industry is building new technologies in the industrial metaverse to bring these ecosystems to life. This brings us to our first keynote speaker, Mo Tanibin, the Vice President and General Manager of Azure IoT and Edge AI at Microsoft. He leads a multidisciplinary organization across engineering, product management, program management, and design. Previously, Mo worked for Amazon and Samsung in several new categories of AI and connected smart products, including robotics, ambient intelligent spaces, and smart appliances. He started tinkering with digital and analog electronics and wrote his first line of code when he was just a young teenager. And since that time, he has developed a respect for and interest in how important design is to the success of a new product. With that, over to you, Mo.
Thank you, Chris. I appreciate the opportunity to be with all of you. I'm super thrilled for this conversation. I think it's very timely, and this is where the world is going. So I'm going to walk us through some notions that today we call industrial metaverse. 3 years from now, we may call it something else, but the underlying technological advancement and trends are real and they're happening. And show how it is working in the commercial world. It's not too difficult to draw basically parallels and extrapolations to the non-commercial world, the world of government, or the other applications that this can address as a software and hardware technology. Before I get started, I just want to define what we call these days metaverse. There are companies that change their names even to reflect how important this technological trend is. But there are 3 types of metaverses that currently exist. One is the consumer metaverse, which is the kind of stuff that Facebook and some of the other consumer-oriented companies are driving. It's about attending events, it's about social gatherings and all of that stuff. Then there is the enterprise metaverse, which is about collaboration and bringing people together within an enterprise and a set of whether government or company or commercial company group of people. Then there is the industrial metaverse, which I believe, and there's data to support it, that it's the biggest value creator of all 3. And this is about physical worlds and digital worlds coming together for the first time in our history, as human history, or our technology development. This is where basically we're digitizing and creating models of the physical world. Then we have digital world also that does a lot of data processing and creating insights. And now we are fusing these 2 worlds for, and they're becoming an incredible value creator, the same way that software became an incredible value creator 50 years ago, but in every aspect of our life. And to do this, bringing physical and digital world together, you need 2 things. You need a very strong cloud platform, and then you need a set of platform functions that bring data from the physical world into that digital world, and vice versa, taking stuff from the cloud side to the physical world for actuations. So we started our cloud journey over a decade ago, and after a while we realized that the real value that cloud will bring, after providing some very cost-effective compute, networking, and storage entities, is actually interfacing with the physical world. And so we started as a company driving the intelligent edge. And to do intelligent edge and intelligent cloud together, which is the foundation of industrial metaverse, you need a set of technologies. IoT is a clear foundation for that, and that's where the data goes from physical world to the digital world and vice versa. Then the networking, and there is a huge inflection point in how hyperconnectivity is enabling us to digitize the physical world, basically. AI is a major component of this, and the digital twin is the representation of the physical world in the digital world. With all of this, we can build industrial metaverse applications. Let me walk us through why this is such a big deal. And again, this is not about the term industrial metaverse. This is about the technological trends underlying this industry shift that are going to change how we interact with the physical world, with other people, and with the technology itself. So, as I said, this is about bringing these two worlds, physical and digital, together. And to do that, the first thing you need to do, you need to model the physical world. And Chris mentioned a few items around the maturity model of this, but it's about basically, I'll mention some of them, how the actual space would look like in a three-dimensional modeling. Then the relationships between entities within the physical world, assets and objects, people. And we do that through an entity called digital twin. Digital twin is, at the end of the day, for us technologists in the room, is a state machine. It can basically receive data from the physical world, and those data, those pieces of data come from connected sensors, various types. It could be a camera, could be a temperature sensor, a vibration sensor, you name it, any type of sensor. It could be a switch. Switch is a sensor. And then it reacts to those because it takes those sensor data as events and then combines them with other pieces of data that may be coming from either digital or physical sources, and creates a new event. That event might be go do something in the physical world, go to actuate. So the first thing is to model this. Once you model it, it's great. The model can be sitting there, but you need to keep it in sync with the physical world. Physical world is dynamic. Things change all the time. People walk around, cars move, robots are in this place or that place, shelves are empty or not empty. All of this need to be captured and turned into events and then get reflected into that digital twin model of the physical world. So the synchronization is where you need a lot of the IoT stuff to do that. But once you do this, then all of a sudden something wonderful happens. You can start doing things that we couldn't do as easily before because the physical world wasn't as hyper connected and in near real time wasn't reflected in the digital world. One is you can track and observe the past. So the data comes in. Data in the physical world, typically events are ephemeral. They happen and they disappear. In the digital world, nothing is ephemeral. Everything stays. So if something happens later down the road, you can go back and see what sequence of events led to that something that happened. It's like almost traveling in time to the past. It's not in that certain context, it is traveling in time in the past. And that is done through a set of services and analytics services that typically are offered as a set of cloud services. Then you can use these data and train models and predict the future. AI and ML are incredibly powerful prediction machines. So once you have this data coming in, you can predict the future. How long before this machine behaves a certain way, whether it fails or not fail or go into high efficiency mode. How many people are we going to get in this day in this particular room of the building? How fast this particular event is going to happen from now. So lots of things seen in the future. It's again like traveling in time, going to the future. And then you can simulate the physical world. A lot of times when we want to simulate a complex system, it's slow and expensive. We have to almost build a full model of it in the physical world. But in the digital world, if we can get the data from sensors, we can build simulation models in the digital world, and then test scenarios, test what if analysis, and cheaply and fast. And there are you're going to hear from some of the people who are expert in these things, like Ansys, for example, that this is a very powerful tool of minimizing risk in building and operating complex systems. And then once the physical world and digital world come together, you can have immersive fused interaction models remotely. So we talked about traveling in time. Now we're talking about traveling in space. And you can basically travel or engage a physical world object remotely in a context that is fused with digital work information through like AR goggles and glasses, or not AR. It doesn't have to be AR necessarily. But all of a sudden, this whole it's almost sometimes when you experience it for a few hours, it's hard to figure out which part of the world that you're seeing is physical world, which part of it is this digital world. It becomes so fused. And this is the world that we're going to operate in, we're going to live in in the near future. And the near future is probably in 2, 3, 4 years, you're going to start seeing the rapid increase in adoption. But a decade from now, this is the world how it's going to look like. So this is basically what industrial metaverse is about. And as I mentioned, the modeling part, it includes the topology of the 3D world. It includes the relationships and symmetric, the geometry, the relationships, and a whole bunch of different types of data that semantically and geometrically represent the physical world in a digital model, which is the digital twin. I give you one example. I'll go this one in detail and then just cover another one fairly quickly. There is AB InBev, which is the largest beer brewery on the planet. They have like Budweiser, Beck's, Stella Artois, Hoegaarden, and a bunch of other Corona, a bunch of other brands. And it's a complex supply chain and manufacturing system, very complex. From the time that the order lands that we want this brand of beer for this market at this much, then you have to assign it to a brewery, a factory, and that alone, because even certain brands, specific brands, when you make them and brew them for different markets, they have to have different tweaked tastes and beer properties, and like they have to taste differently. And during the brewing process, you have to monitor closely the chemical characteristics of the beer, pH, humidity. There is something called apparent degree of fermentability, ADF, and all of that. And there is a person who does that in almost near real time, watching this big pots on the brewery floor. Her name is Brewmaster. And brewmasters are very in demand, very skilled, takes years to become a brewmaster. They go and test it, taste it, all that, and make sure that this pot, a huge pot, is being brewed by the spec that is needed for this order. Now, Microsoft and AB InBev got together. We completely digitized the whole brewery factory floor, the ordering, the shipment, and the supply chain once the beer is ready to be shipped, all of that into an industrial metaverse with digital twin and all of that. And now going back to why this is such a big deal, one brewmaster can operate remotely. Many breweries can manipulate this pot or that pot if it needs more water or needs more this type of chemical or that type of chemical. All for all that, it could be sitting in a vehicle doing all of that. And that's the power of industrial metaverse. That all of a sudden your whole supply chain and production and complex physical system is within your reach remotely. You can look back historically, you can look to the future and operate it in the most efficient way. I'm going to show us a video of this, how this happens in AB InBev, and then we're going to go to another quick example.
100 breweries, and 160,000 employees across the globe, Anheuser-Busch InBev is the largest brewer in the world, with an unparalleled portfolio of brands and a global presence with operations in 50 markets. AB InBev is an expert in their field, and their forward-leaning and innovative spirit is leading to new breakthroughs in brewing. Through their digital factory and supply chain of the future initiatives, in collaboration with Microsoft, AB InBev is focused on transforming both breweries and their global operations by empowering their frontline colleagues with digital solutions that enable world-class manufacturing, mobility, data automation, and business insights. It begins with the brewery coming to life with AI, Azure Digital Twins, and the Microsoft Cloud. The brewmaster is responsible for making the best quality beer. She has unprecedented visibility into the brewing process, so she can predict and monitor the complex chemical and biological fermentation parameters required to produce the highest quality product. Frontline operations can remotely monitor critical quality and traceability data from the manufacturing execution systems using the mobile brewery technology built using Azure. With built-in energy and utility management solutions, the digital brewery supports AB InBev's industry-leading sustainable development goals. After the perfect batch is ready to be bottled and shipped, AB InBev extends their digital twin solution to support the packaging line operations to ensure it's done right. These can plants are adopting Azure AI and Microsoft Project Bonsai's deep reinforcement learning to deliver line balancing optimization that detects and automatically compensates for bottlenecks in the complex can manufacturing operations. At AB InBev, their 100% uptime mindset is enabled through predictive maintenance and global support. A frontline operator can efficiently address problems through remote collaboration with a maintenance technician, ensuring no unplanned downtime of packaging equipment. The perfect beer is packaged and ready. The digital technologies of the AB InBev supply chain of the future minimizes carbon footprint while making sure the right beer gets to the right customer at the right time. This beer's journey is complete, and AB InBev and Microsoft are taking bold steps into the future.
That's just one example. As you can see, very complex system in the physical world coming to the digital world. It's not hard to look at it and say, okay, the same thing can be applied to any other complex system like a nuclear power plant, or I don't know, aircraft carrier, or things like that. The other example is BP doing basically creating the industrial metaverse for their oil platforms. I'm going to just skip these ones in the interest of time, but that has given them, using this has given them huge visibility into carbon footprint reduction or increase as their operation configurations change. The next one is also another complex supply chain, which is the group of Bimbo, very large bakery, global bakery, about 196 bakeries across 30 countries. As you can see, food has certain sensitivities, and you have to be very careful about if something happens in this supply chain. It's very valuable to go back and see where was the source of this something, whether if for example a bad batch was baked, where did the issue come from. Now let's take a look at the left side of this slide. So if to do the industrial metaverse, certain capabilities you have to put together to bring it. Obviously you have the physical world, you have to model it, you have to synchronize it, then you have to have a set of analytic services to track and look into the past. You have to have a set of AI and ML capabilities to predict and simulate and autonomously control. And then you have to have a fused level of interaction. And then when you look at on the right side, these are various offerings that Microsoft and Azure platform has to offer those capabilities. And in the highly secured enterprise space, which I qualify government applications as some of those, Microsoft probably is one of the leading companies who can bring all of these pieces together. I don't want to turn this into an information, but I just wanted to kind of let you know what it takes to build some of these things. And then, as I said, LEO satellites and networking, evolving networking, 5G technologies are basically pushing industrial metaverse ahead and accelerating their development and adoption. Then it takes a lot of other pieces of technology in partnership to build these industrial metaverses for data contextualization, simulation, visualization, like even game engines come to play, as you can imagine, and physics engines in games to build all of these end-to-end systems. So with that, I'm gonna conclude my part of the conversation, and I don't know if we have time or not for a few questions and Q&A. Would love to answer any questions that we have.
Thank you so much, Mo, for an engaging presentation. Our first question is, the metaverse and digital twins clearly provide value, but when does it make sense to make this investment for our federal assets?
That's a really good question, and it depends on a lot of different things. Where is the mission of the organization in terms of benefiting from this type of technology? Some organizations are more kind of conservative, if you will, and they want to wait until a technology is fully proven and it's ready and used and tested by everyone else and then adopted. And some, because of the criticality and sensitivity of the mission, they need to be ahead of the pack. So if your organization is one of those conservative ones, I would say maybe a few years, as I mentioned, 2-3 years, maybe 4 years, it's going to start picking up. If you are on the adoption of leading edge technology, which some of the very sensitive government projects and products are, then I think the time has come for sure. And it's like any other technology. When it creates economic value, it's adopted. But about 45, 50 years ago, we learned if we combine silicon and software together, we lowered the cost of a very, very valuable economic input, which was arithmetic. Arithmetic from silicon and software was much, much cheaper than arithmetic from the previous source of arithmetic supply, which was human. Humans were more expensive. And because when something gets cheap, economy drives it for adoption. The same thing, this is another kind of inflection point in technology. We are doing things that have been very expensive, difficult, and error-prone in the past with this marrying physical and digital world through software and hardware and sensor and networking. And the economy is behind it. So as I mentioned, doesn't matter what we call it, there is an economic force behind this adoption. And my guess is 10 years from now, this is going to be commonplace pretty much everywhere.
Thanks, Mo. I think we have time for one more question. And the other questions we probably won't be able to get to live, but we will shoot them to Mo offline. But the next question is, what are some of the biggest challenges you're aware of when it comes to getting a customer to see the value in a digital engineering approach and the metaverse in general? And what are some successful strategies you've used to overcome hesitancy?
So that's a really good question. Some of the challenges that we have and our customers have, we're basically adopting the same technologies for our own campus. In Redmond, Washington, we have a very large campus, over 100 different buildings, and it's like a small city or a village. And we're digitizing all of that into this model. The physical world has evolved into a very sort of diverse, read it, fragmented, different types of technology. And bringing all of that together as sources of data in a common platform to be consumed by data analytics and AI, that alone is a lot of work. So there's technology involved that needs to evolve and needs to be adapted. But there's also culture, there's mindset. I remember I was talking about industrial metaverse to a very large, complex supply chain in the world that does overnight delivery and things like that, as you can imagine. I won't mention the name, but you can probably guess. And I was talking about these automation and everything, and someone in the audience said, well, we are automating everything already. Why do we need this? And then I was curious. I asked, how are you automating it? And he said, well, we're using Excel macros. So changing that cultural mindset that we are basically transitioning to a new world of technology is another challenge. How it works, I think the best kind of model to overcome both of these is to show early wins. Pick up a really, really critical use case that there is energy behind it, that we have to solve this no matter what. In a focused way, build the application for it, show the win, show the success, and then both cultural and technology adoption development challenges, they almost fade away once there is a success that is visible and tangible.
Well, thank you again, Mo, so much for your time. There are some really great questions, Mo, that we will shoot you offline from our Q&A panel. And let's take a look at some of the digital engineering and digital twin projects that are going on at Idaho National Laboratory. So we're going to play a quick video.
Thanks, folks. Great. It was great to be with all of you.
Thank you again, Mo. So we've looked at kind of a quick overview video of some of the digital twins that are going on in the DOE space. And INL and our partners at the NRC have invested over a decade of research into our MOOS multiphysics platform. Furthermore, we've dedicated the last 4 years to building a full digital thread system that we now call DeepLinks to build a digital engineering design and autonomous digital twin ecosystem. This work has culminated in the first autonomously controlled non-nuclear microreactor, which we will actually show you right now through the streaming service.
Idaho National Laboratory built a virtual model or digital twin of Magnet, a non-nuclear microreactor technology. Recently, researchers performed the model's first live test. The digital twin successfully performed autonomous control of Magnet. Using machine learning, the digital twin was able to predict future heat pipe temperatures. With these predictions, the digital twin successfully detected trends toward arbitrary threshold temperatures and autonomously controlled the heat pipe, thereby changing its temperature without any human intervention. Researchers were able to monitor the digital twin through both a traditional user interface as well as through a Microsoft HoloLens. The HoloLens provided a 3D model of the heat pipe, including sensor temperatures. Researchers are continuing to build from this experiment to create digital twins that can enable self-adjusting, cost-efficient, and safe microreactors for the future.
All right, welcome back. So now we're going to introduce our DOE leaders for our first panel. So panelists, this is a great time to come back onto video so we can start our panel session. So the first person we introduce is Craig Sloan, and he is now on the screen. He is the director of NNSA's Office of Proliferation Detection. In this role, he leads efforts to advance U.S. capabilities and expertise to detect and characterize nuclear proliferation and nuclear weapons development activities detect and respond to nuclear threats, and monitor future nuclear arms control treaties. Our second panelist is Dr. Jen Schaefer. She is the program director at ARPA-E and a professor at Colorado School of Mines. She currently manages the GEMINA program at ARPA-E, which is focused on development of digital technologies relevant to advanced reactors. Our third panelist is John Alardi Parrish. He is the federal program manager for NNSA's Stockpile Management Product Realization Integrated Digital Enterprise, or PRIDE program, as it's more well known, and NNSA's adoption of digital engineering. In that role, he's largely focused on building the NNSA digital thread and ensuring we are integrated in our pursuit of digital engineering goals across NNSA. Our next panelist is Rihanna Shinasa. She is the chief engineer of the Biotechnologies Office in ERE. In this role, Rihanna is working on addressing key challenges to the integration and scale up of bioenergy technologies. For over 20 years, she worked at Valmet, which is a global developer and supplier of process technologies. Rihanna is also an adjunct professor at the Department of Chemical Engineering and Applied Chemistry at the University of Toronto since 2014. And our final panelist is Stephen Lee. He is an applied mathematics program manager in the DOE Office of Science, a co-chair of the Artificial Intelligence R&D Interagency Working Group, and he's leading several DOE efforts in scientific machine learning, artificial intelligence, and digital twins. So thank you to all of our panelists for joining us today, and we're going to kick off right away with our first question. So Craig, the defense nuclear nonproliferation community has become leaders in new applications of explainable machine learning across the DOE complex. Recently, DNN has begun investing in digital twins as well. Can you share some current areas of research, and do you foresee a similar leadership role in the emerging areas of digital twins for DNN?
Hi, Chris. Thanks very much for inviting me, and thanks to you and the organizers for putting on this event. Looking forward to the rest of it. So let me answer your second question first, right? The short answer is yes, absolutely. I see this technology as becoming more and more important down the road here, and there's a couple of reasons for that. And I think by explaining the projects, I think I'll be able to explain why I think this is an important technology. So we've got a couple of efforts ongoing right now. You showed two of them. And it's a little bit awkward that I'm going to describe your project to you, Chris, that we fund you to do. So at our next quarterly meeting, you can correct me if I say anything wrong, right? But I'm actually very excited about Chris's project because what he has done and he and his team have done and you saw it there, where they were developing a digital twin for several different advanced reactor designs. And it's really, the goal of that is to really aid in thinking about how the IAEA, or the International Atomic Energy Agency, could use these digital twins in support of this mission, either by identifying and training inspectors on diversion scenarios, or in the future, interpreting data they receive from a safeguarded reactor. So really excited about that. And starting this year, in this fiscal year, Chris will actually be working with Idaho State University to sort of test it out with their reactor there to sort of mimic some diversion scenarios and see if the digital twin they develop can detect those in real time. So a red team, blue team kind of scenario. So really excited to see how that turns out there. Another project we're developing a digital twin for is at Oak Ridge National Laboratory, which is with their Radiological Engineering Development Center. That is the facility where they actually recover isotopes of interest that are produced in the high flux isotope reactor. And so again, this says it safeguards applications for it. So that digital twin, Mike Dion from Oak Ridge is the PI for that, is really investigating effluent production, chemical speciation, and abatement for off-gas transport. Again, from an IAEA perspective, a digital twin of a similar facility could be of value to them, say under a wide area environmental sampling scenario, right? So I think those are some of those higher level digital twins that you talked about in your introduction. But there's some other digital twins when you describe digital twins, and I think they have a potential role in growing and maintaining nuclear nonproliferation expertise at the national labs and elsewhere. So our nonproliferation stewardship program is focused right now on developing infrastructure, both laboratory and computing, to provide researchers at the national labs and interagency partners with hands-on experience with technologies that could be used in the development of a nuclear weapon. But modeling is an important aspect of that, and digital twins could be a useful component of growing that expertise. And you showed the Beartooth digital twin that you're developing, right? So Beartooth is going to be this test bed where we're focused on plutonium production. The modeling that digital twin or developing that digital twin is going to be in production, the developing digital twin is an important aspect of that project there. So to get back to your second question, I just see the need for these digital twins and this technology growing in the future. And we should be leveraging the capabilities that industry and academia are investing in.
Thanks, Greg. So Jen, over to you. Gemina has realized a collection of Generation 4 digital twins within the nuclear industry. Can you share some of the highlights of the Gemina program, and where do you think ARPA-E should push for innovation next?
Right. So, and thank you so much, Chris, for inviting and organizing all of this. But so there's a couple of different highlights, or if I really want to say maybe vignettes of the program that are maybe helpful for orienting folks to the technology in different ways that we can think about it. One example of these types of digital technologies is high fidelity computational fluid dynamic simulations that really provide you great precision and prediction of where some of the stress points might actually be in your facility. So classically, when we think about maintenance of a facility, you're kind of playing a little bit of a guessing game as to, where really might we be having issues and where should we be putting sensors, and this is all driving your maintenance plan, right? Alternatively, if you have really high quality simulations, then this can be something that helps inform your sensor placement. Maybe are you actually using less sensors? And then it's also perhaps informing actually what your maintenance strategy could be, because now you have a better physical sense of really what the strain and shear is actually on your reactor facility. So that's kind of one application of it. Another area where we're seeing some excitement is actually thinking about less on the high fidelity side, but more on actually digital engineering with respect to construction. And in that regard, it's kind of a different level of high fidelity, because we're seeing that teams can maybe put together in real time what's happening with the development and deployment of construction of large sites. And being able to scan facilities and really being able to accurately assess what are the needs for various joints or bolts, or what happens when your shipped technology is actually different than what you would plan for, and being able to inform what was happening elsewhere in your supply chain and help all of your construction partners see this in real time. And I think that that's also a very important aspect that we've been looking at here. Other areas are things like reactor companies that are broadly using digital technologies to improve maintenance, operations, security, and really pull all of this together in more of an umbrella portfolio. Or even, basically improving maintenance strategies with respect to more aggressive conditions like molten salts, and being able to manage effectively in those realms. And so those are areas where we've been able to, push within the Gemina program. Where do we see this going in the future? I think one of the most critical things that we can do as far as next stages is we're starting to see that we can develop the digital platforms. Now we need to start interfacing these again back with the physical system, maybe in thinking about how subsets of these things piece together, so we can start testing and validating, what the perception of our simulation is, and matching that up with the real world and get that data linked up. So that's basically where we're at now.
Thanks, Jen. So John, NNSA Defense Systems, you all are building that modern digital thread ecosystem, which I mentioned in your bio, across multiple laboratories and sites. Can you share some of your current progress in building that ecosystem, and how can we lay the groundwork to really collaborate across all those different laboratories and sites?
Yeah, sure thing, Chris. So within NNSA, we have about 10 to 20,000 professionals working to sustain the stockpile. And we're hoping to modernize our digital thread to really connect the major workforces across the product lifecycle together in an integrated fashion in order to increase our engineering productivity and enable kind of rapid cross-domain cycles of learning. I tend to simplify this down to changing our engineering designs to achieve a broader range of goals and objectives. And that could be better manufacturability, easier maintainability, lower lifecycle costs, or faster time to market. And we have three main approaches that we use to do this, right? We talk about creating enterprise-wide authoritative sources, changing the artifacts that engineers produce to be more digitally consumable by others, and changing our business processes to take advantage of those new digital capabilities. So within Pride, we've been working to establish new enterprise-wide authoritative sources. So this is cross-laboratory, cross-plant. And in this past year, we stood up our the first common requirements management capability, really focused on better feeding requirements data further down into the lifecycle for downstream uses, as well as enabling more integrated and automated approaches to requirements traceability. Another big area, kind of talking about changing our engineering artifacts, we've invested a lot to move our mechanical part product definition from two-dimensional drawings to 3D models. While relatively simple in concept, the current standard produces a big bottleneck in how our designers and our manufacturers work together. So in this past year, we've established some new standards for those 3D forms. We're updating enterprise policy to begin enabling the use of those. We're ensuring that our digital systems and business processes are capable of handling this new form. And as we round the corner on that, it should enable deeper forms of design for manufacturability, model-based manufacturing and quality, and a host of other digitally native kind of analysis functions. So how can we lay the groundwork to collaborate? I think as an organization, we need to build our muscles to integrate across the complex, right? Which is, we've got some key principles that I think we need to adopt in order to move together. Moving from those document-based data to more model-based engineering work products, dropping barriers to human and algorithmic collaboration. I think it's important for individuals to really participate, establish, propose enterprise-wide integrated groups or initiatives in your area in a manner that integrates with your peer subject matter experts. And oftentimes what I find is we have a difficulty as an organization imagining better ways to operate. So it's incumbent upon all of us to really advocate for what that future should look like to get people really dreaming about it. So we do have a number of existing and emerging venues for that across the complex. From MBIT, we've got various digital engineering and model-based projects ongoing across the sites. And within Pride, we're establishing more enterprise stakeholder committees to bring together the complex. And there are a whole host of other kind of internal and cross-site collaboration initiatives existing today that can get you involved. Thank you.
Thanks, John. So over to Rihanna. What are some of the most significant challenges to scaling up the production of biofuels? And where do you think digital technologies can play a role in scale up of those technologies?
Thank you, Chris, for inviting me. We at BITO believe that, of course, there are different risks associated with feedstock, with capital investments, but I'm going to only concentrate on the technology part. The most significant challenge, in my opinion, is keeping systematic and methodic scale up. It means that, in our opinion, we have to do it one step at a time, and if I have to repeat a word, it's piloting, integration at early stage, and learning from what we do before going to the next step. So then you can see how digital engineering can come into play. Multiple new technology steps equate to higher risk, so increasing the need for integrated pilot staging. And there is high value in fully integrated pilot testing for developing the design and evaluating process parameters for these new technologies. If you have commercially available off-the-shelf equipment, unit operation, they do not necessarily integrate easily into new technical processes. So, and we all know, as an example, how feeding solid biomass to reactors continues to be a challenge. So basically, what I think history has shown us is that we should not learn whatever we can learn in smaller scale and leave it for larger scale, and which would be more costly and time consuming. We should minimize project operation risk through fully integrated piloting in a manner close to commercial. Some people call it scale down rather than scale up. And as I am talking about this learning and going from one scale to the other, then the digital engineering is obvious. It's how it can be used. Scaling up should be according to the rules in chemical industry, not necessarily in electronics when things are much faster. And never miss a step. So if we use modeling and digital technology to learn the process data for each scale, this helps to optimize a given scale, and with the design optimization of next scale. And the use of digital engineering will help in using the lessons learned in each scale before we scale up. If I look at what, for example, if we are thinking about some key challenges in pre-treatment of biomass, something that INL, Idaho National Lab, is our expert and is working on: biomass freezing, sizing, moisture content, solid handling, all of that. Now, imagine what Mo was explaining to us today, that model this physical world, synchronize it with the physical world, track and observe what we have seen in smaller scale with these units, and then predict what can be in the larger scale in the future. And so I really believe that we can, with the basic engineering of like sense for chemical engineering, and with the digital engineering of the future, we can make this road much easier to scale up for biofuel production.
Thank you, Rihanna. So over to you, Steve. I know you're working on a study with the National Academies of Science, Engineering, and Medicine on digital twins. So looking outside of energy and defense, what do you think this audience can learn from other digital twin applications?
Yes, thank you for the question, Chris. So this, as Chris mentioned, is a National Academies Fast Track 18-month study on foundational research and future directions of digital twins. We're all excited about digital twins and potential applications, but the DOE is going to focus on what are the foundational research needs and challenges that we need to address to enable a diverse range of applications. So this report will lead to 3 workshops and 4 reports over the next 18 months. And the 3 application drivers are climate science, biomedicine and digital humans, and also aerospace engineering. And the hope is that by looking at these very diverse applications, that we'll be able to identify what are the foundational research needs and what are the building blocks for enabling us to build and scale up digital twins to address a wide range of applications. So we really do see digital twins as these sort of interactive computational models with AI that can learn from real world data. Now, that's a lot, that's a mouthful, and to get all those parts and pieces and technologies working together, there's some key foundational mathematical, computational, statistical research areas that will need to be addressed. So the study will look at definitions and use cases. What are those research gaps? What are some best practices and for digital twin development and use? And then how do we move forward? How do we take advantage of these advances in technologies to benefit, Department of Energy, Department of Defense, and society in general? Thank you.
Thanks, Steve. So this question's for the whole panel. Maybe we'll start with Craig, but we'll move around. Is as we develop better digital models, do you think physical testbeds will retain their importance for validation or just become less important over time?
I think they will absolutely maintain their importance. I think to some extent it's a, I don't know if trust is the right word, but I think you're going to need that validation from the actual physical test beds, right? You're going to get people will, I think for some time to come, are going to still need that confidence that a physical test bed will provide them in understanding the value and the role of digital twins. So I don't see that going away anytime in the near future. Certainly my office is going to be still investing in test beds, and we're actually developing, as you know, Idaho is developing a digital twin of one of our upcoming test beds. And so I see that being very important in the future. So.
Yeah, I think, Chris, I might add on that. Oh, sorry. One of the things that when it comes to digitization of, kind of the real world is it happens in almost a very iterative way, right? Somebody else pointed it out to me, but right, with Google Maps, right, it started off as, lower fidelity than it is today. And so as we think about how our digital world evolves, right, there's going to be a pretty long period where we maybe digitize a component, but then we continue to add features and evolve it. And so for some time, I think we're pretty far away from not needing that validation from the physical world in what we're doing.
Thanks, John.
Yeah, so I'd like to add, I know within NNSA we talk about, we have a limited classified production capacity, and so we're hoping to use models to really change what we're testing, or our tests from less kind of exploratory tests to more confirmatory tests. So, if you pay a lot of money to do a big physical test and you find something's drastically wrong, you're gonna have to go back and redesign it. But if you get to that physical test and it performs just like it did in simulation, it has the ability to greatly accelerate. I think the other piece is the modeling can also focus us in on more limited testing in areas where we have less confidence in the digital models. And so I think the flavor of physical tests should evolve over time. But I agree, I don't think we're ever gonna stop validating that our digital models meet the real world.
Thanks, John. So we actually have a specific question from Eric Lynn in the audience. I think, Steve, we'll start with you on this one with your mathematics background. How do you get a usable digital model that can be used to make actionable predictions? Do you use reduced order modeling, ML surrogates? What's the cutting edge approach?
Wow, that's a great question. And I would say all of the above and then some. Certainly in our applied mathematics program at GOE, we've pioneered this idea of scientific machine learning and AI. And that looks at, the areas you mentioned, reduced order modeling, surrogates, but also optimization, differential equations, and a bunch of uncertainty quantification. These are all key areas that need to come together to build, real-time, reliable, trustworthy models and digital twins. So there's a lot of research challenges ahead. The National Academies report will help with that, but there's still some breakthroughs that will be needed.
Thanks, Steve. And we have another question for the audience, for Jennifer. So Gen 4, small modular and mobile microreactor market participants are right now focused on what you have already mentioned, linking digital engineering to digital execution to digital operations and maintenance. We're also seeing a realization that while that focus brings significant benefits to the first or demonstration plant, but an order of magnitude benefits to the design and construction of the second, third, fourth, nth plant as well. Will you comment on the nth plant as well as fleet operations and digital twins?
So if I think I understand basically what all of that is getting. Right. So basically kind of the idea being that when it comes to microreactors, and in fact Marvel, you guys had a demonstration on this, right? And it's linking, and so I think it's really kind of connecting this, not necessarily on the microreactor scale, but then also, the bigger scale as we move forward with this. But also, I think part of what they alluded to at the end there was sort of end user application and getting this all in a way that it's not necessarily just at an R&D level, but actually at an executable level that people can really kind of work with. And, say, for example, the NRC believes what, is being, just because you're able to do it on one site doesn't necessarily mean that the regulator is going to have buy-in on this. And so that would be probably where interface would happen next.
Okay, great. So one other question came in for Rihanna. As we tackle the problem of our generation, climate change, what is the optimal relationship of government and industry to realize a net zero future? What role do you think the national laboratories need to play to solve those challenges?
Thank you, Chris. I believe the industry should work as a market pool, and the government should assist with de-risking new first-of-a-kind technologies. So the market pool and industrial engagement and leadership are essential in guiding the government to spend all of its resources on the most impactful path. And by industrial engagement, I mean real skin in the game. Even when we have a FOA or in project that is like 20% cost share, it will be helpful for the industrial partners to help in designing the experimental work, planning the project, and then help with analyzing the data from their own perspective. And for larger projects, I believe they should have project deliverables and budget. But generally speaking, I think that industry should lead, and government and national labs should help and enable with national labs or the best resources we have in the United States for pushing the technology and making it accessible for the industry.
Thank you, Rihanna. So we have another question for the whole panel, and this may be our last question, but if someone has one more, we will we'll try to see if we can fit it in. So for the whole panel, one gap I think, and this is from Mohammed, is sometimes that is overlooked is licensing. At least in nuclear applications, I think we need to invest more in explainability as well as validation and extrapolation so digital models can be licensed. So I guess the question is, do we need to invest more in explainability methods for artificial intelligence? Maybe that's a good question to start with Steve or Craig.
So quick question is, of course, this idea of UQ, uncertainty quantification, verification, validation, those are key components of what we do at the DOE Office of Science, and I think across the DOE laboratories. So we'll certainly need to continue in those directions.
Yeah, if I can just add something, Chris, on that, on the explainability, it's absolutely an issue from an non-pro perspective, right? You can't, you know, an analyst in the intelligence community or DoD they need to be able to understand the answer that comes out. It can't just be a black box for them. They need to be able to understand how the algorithm came up with the answer it did. So in that sense, explainability is an incredibly important part of what we're doing here in DNN and NNSA.
Sounds great. So we have one final question we will ask. And this would be for the entire panel. So what do you see as some of the most valuable applications of digital engineering going beyond visualization towards higher levels of interaction? So this is a visualization focused question.
Well, I'll just quickly say one of the driver applications for the National Academy study is climate science. So that's if digital twins can help us better understand the effects of climate change, make better predictions, develop mitigation strategies, that's a game changer.
Thanks, Steve.
Yeah, and while certainly visualization is a really helpful tool, especially when you're doing construction, right, and getting that locked in. We actually have the opportunity here to run forward and reverse scenarios, and this becomes incredibly important if you're operating in the security space, if you're evaluating and operating, in operations and maintenance. And so I think this is where we're going to start really seeing compounding effects of our ability to leverage these tools.
Thanks, Jen.
Yeah, I think from my perspective, it may sound a little bit more mundane compared to digital twins and visualization. We do really big billion-dollar, tens of billions of dollar projects over a long time. And just, let's see, from my computer science estimation books, having good requirements versus having just average requirements adds something like 40% to the overall project cost and duration. So there's a lot of investment now in things like model-based systems engineering. How do we analyze that we have the right requirements? We're looking at how do we manage requirements to know that we're flowing down the requirements and we can defend kind of the build back up that we've delivered on the requirements. And so while it seems like a very basic business process thing, I think it is hugely impactful to large engineering projects. Thank you.
Thanks, John. Any final thoughts before we close?
So if I could just connect back to Mo's presentation about the industrial metaverse, I think we'll be able to take advantage of emerging technologies such as better sensors, the appearance of more wearables, whether they're glasses or headsets. So, and the next generation of the internet is going to be more interactive and immersive. So we really need to try to stay ahead of the game in terms of really visualizing how we might be able to take advantage of those technologies. And I think that first presentation was a good way to kick things off.
Thanks, Steve. Anyone else have a final closing thought?
please make it more affordable. I'm just thinking how wonderful it would be to have a digital twin next to a pilot plant so that we get all the information and help it for the scale up. But I think it would double the price of pilot plants. So I'm looking forward to a day that it will be affordable.
Thank you, Rihanna. So I think that brings us to a good close. We are exactly at 12:05 my time, 2:05 Eastern. So I want to thank the panelists. These really are the leaders within the DOE federal space. And I thank each of you for spending 30 minutes with us today to go over, and what they don't know, the hour and a half that goes into making this actually possible prior to this. So I really thank each of you for coming here and spending your time with us. Hopefully it's been helpful to everyone from our laboratory partners who's joined to see this presentation. So thank you to each of you. And we're going to take a brief break and show a video from Sandia National Laboratories on some of the work that they are doing in digital engineering, which I think is related to some of the work that John discussed earlier. So thank you to all our panelists.
Thank you.
Thank you.
Thank you.
Let's queue it up. One moment as we queue that back up.
Hey, Chris, I'm here to answer any questions too if they come up.
Okay, great. And that is Anthony Mata, by the way, who is a senior manager at Sandia National Laboratories. And they are doing a lot of great work, by the way, in digital engineering. I think the video is trying to load. Of course, as we're live, Anthony, it doesn't want to. But
I'm just a manager, though.
So maybe for the sake of time, Mike, if you're on, maybe we will go directly to the DOD panel, sorry, and we will retry playing this after your panel. So Mike, over to you.
Yeah, absolutely. Thanks, Chris. And if I could have Ben, Daniel, Eric, Nick, and Andrew, to the extent that you are able to both come on camera and come off mute. Great to see all of you. Chris, this has been awesome. Let me just first say, I've been really fascinated by a lot of the technologies and capabilities that are already happening both in the private sector and with Department of Energy investment. We're going to do a slight variation on that for this group of folks from across the Department of Defense who are working on innovating within what I always call the world's largest bureaucracy, which is actually doing it a short service. It's a system of bureaucracies, of many, many bureaucracies, of which these are the sort of innovation fire starters. And so while many of them are thinking about and applying actively digital engineering tools today, some of them are maybe not. But our hope is that through this conversation, one of the things that we can do is that the technical experts in the audience from who are receiving this message are building things that are meeting the needs of the Department of Defense as we work to fight and win our nation's wars and defend the homeland. So please keep that in mind as we're providing this context. But I'd like to kick it off first with Daniel Hetzma, who's the Director for Digital Engineering, Modeling, and Simulation at the Department of Defense. So Daniel, you are the one who is actively working with digital engineering tools today, in particular, in thinking about how, in a broader strategy, both on how those are applying to our forces today, but also how they are, we may have a video, 1 second. But also about how those are leading to a thriving digital engineering ecosystem for future capabilities as well. So I wonder if you would just share with this group, how you're thinking about both of those sides, both of those strategies. One on how you're investing and applying digital engineering tools to help our forces today, but also two, what are you looking for partnerships from the private sector, from national laboratories, and from outside stakeholders that could be really important in the future?
Well, first, I just want to say thank you, Mike, for having me as a panel, and Chris Ritter for inviting me to this wonderful event. It's an honor to share the stage with such wonderful leaders in the digital engineering federal government kind of system. And even Mo's talk earlier about kind of how the digital twin and the ability to track and observe the past and then use that data to predict the future. That was such a great insight that I really resonated with as we talk about the power of digital engineering. So really, for your question, I kind of want to remind people that the digital engineering strategy that the DoD produced is actually 5 years old now. It came out in 2018. Since that, we've actually seen a lot of great movement going on. The DoD has really moved into implementation and stepped out of just kind of broad strategy. Each of the services and various agencies across the DoD have started developing implementation plans and actually have really started moving out. One of the great examples we can see of something like that is from the former Assistant Secretary for the Air Force, Will Roper, Dr. Will Roper, and his paper that he wrote, that there is no spoon, just that new digital engineering, that digital acquisition kind of approach. And so we're really seeing a lot of programs being born digital that's shaping the way we think about what the art of the possible is as we start going from concept through development into operation support and disposal. We can even look right now at some of the recent highlights from the news. So recently, North Korea just did a launch of a missile right over Japan. And so if you guys are aware of some of the key DoD agencies, we have the Missile Defense Agency. And we recently did a kind of a data call, and we found out from them just how they're using modeling and simulation in a broader digital engineering environment to really enable them to better understand and analyze existing and emerging threats. And so that's just a great example that we see where the Department of Defense has now really dove into doing a lot of this. So we're now kind of moving into what I like to refer to as a new chapter of digital engineering, where we're moving out. Each of the services have now offices or programs that are very much transition offices, be it digital engineering transition offices or just broader digital transition offices. Internal to the Office of the Undersecretary of Defense for Research Engineering, there was recently a reorg where Ms. Shu elevated systems engineering and the kind of scope of digital engineering to actually report direct to her. So that shows you the importance of those kind of key enabling technologies as from that perspective, that it was elevated up a level. With this new chapter, we kind of have a new focus. So when the DE strategy was written, I like to joke that the DoD could hardly spell MBSE. Now I feel like maybe we get it right 3 out of 4 times. So making a lot of progress. That's a little joke for you guys. But we're really now seeing a lot of integration where services and programs are combining digital engineering with AI and machine learning, and added to manufacturing, where they're really getting data quicker to decision makers. So moving those milestones in so we can deliver capabilities faster to the warfighter. So we kind of have now internally 3 key themes that we're focusing on: knowledge sharing, policies, and standards. So a lot of what we look at is guided by the principle of how is this advancing digital engineering. So for knowledge sharing, we're very much focusing around trying to support getting the digital engineering best practices and lessons learned out. And that's just more than out of the DoD sphere. We're trying to actually keep it open and actually enable knowledge sharing across the entire federal government. And so we're actually standing up a digital engineering body of knowledge, similar to some of the other great successes in body of knowledges, be it the systems body of knowledge and some of the other more DoD focused ones. And what we actually have a modeling and simulation body of knowledge to continue to help do some of that. For policy side, the DoD, we're actually in the process of doing final coordination for developing a new digital engineering policy that, in simplistic terms, kind of basically requires programs across the DoD to include something digital engineering. So we're really trying to be a little bit of that forcing function to help advance a little bit for any of the few stragglers. We're seeing, like I said earlier, a lot of movement down. And then we're working with DAU to actually incorporate a lot of workforce standards. So that would be things like digital literacy competencies, more specialty ones around digital environments operations, digital environments support, modeling and simulation. And so we're really thinking through how do we enable that entire workforce, kind of the old adage of a rising tide lifts all boats. And so where do I think kind of the labs can help? Well, I really go back to the DoD strategy, which is maybe right there, if I'm pointing correctly. It's goal 3, that incorporate technology innovations. So the labs are really you guys are the forefront. You have the ability to do great innovative things. And really, I want you guys to keep us aware. So at the INCOSE International Symposium, I saw a great talk from Idaho Labs, Mr. Browning, the automation through digital engineering and digital twin. Awesome talk. That's an example where we're expecting the labs to demonstrate and bring that kind of proof of concept technology innovation in. And then obviously for the knowledge sharing, getting you guys to capture and really bring out to the community a lot of the lessons learned. So we're not just observing lessons, we're really actually learning them.
Awesome, Daniel. That I think is a great overview and an understanding about like what the sort of overall collaboration strategy is. I wonder if we could turn to something a little bit more service specific and on the ground level. So I'd like to introduce Eric Riesenbrock, who's actually joined us by phone. And let me just confirm, Eric, you are on and able to communicate?
Yes, I've got you.
Awesome. So Eric is a good friend, but also the lead principal engineer for Future Force Energy and Power at the Air Force Research Laboratory. Eric, I know you have recently transitioned from a position within AFRL's Digital Transformation Office in thinking about how the Air Force is applying some of these tools back to something that's more focused on integrating and furthering really innovative energy technologies. So I'm just curious about, what that transition looks like within a particular service, and what ways in which are you seeing the kind of crossover from the Digital Transformation Office into the work you're doing today, and what ways in which could you see that sort of accelerating in the future?
Sure. Thanks, Mike. And apologies all for not being on camera. We still have our digital challenges here in the Air Force. It's preventing me from accessing some of the systems on my government computer. To start with, I think Daniel nailed it, right? So digital transformation of the Air Force is all about delivering capabilities faster, right? So when I talk digital transformation, I always talk about, hey, there are a lot of technical components to it, but at the end of the day, it's about integrating all of that digital technology into every single area of our mission, which fundamentally changes, right, how we operate. It drives process changes. It drives those business model changes. When we talk digital transformation on the Air Force side, so the transformation today is primarily focused on those acquisition and sustainment communities. So we're really talking that, traditional weapon system development. To give a little bit of background, right, we kind of break it into 4, buckets. So there are the model-based systems engineering, the analysis, modeling and simulation, CFD, capabilities. There are visualization, and then there's the PLM, product lifecycle management tools, right? So those are really kind of the big buckets that we talk about for those digital engineering type tools. And like I said, digital tools provides us with that really amazing opportunity to collaborate, across those weapon system acquisition communities. And, one of the things we see in the bureaucracy that we have in the Air Force and, across the services, right, is it really gives us the opportunity to open up some of those currently stovepiped communities to collaborate in a way that we can use the same language, we can use the same style guides, we can use the same ontologies, things that are really hard to do, right? Because some of those stovepipes are built around specific semantics that different organizations use. And we spent an amazing amount of time really just translating requirements between those communities to ensure that we're all talking the same language, which that slows down, I think as Daniel mentioned as well, slows down that process for weapon system acquisition. So when it comes to energy projects and how I'm, leveraging a lot of the work that's been done in the Air Force that I worked on, whether it's tool deployment, infrastructure development, every piece of the digital transformation, a couple of quick examples. So there are kind of the more mundane things. If you look at, projects, like I said, how do we do that translation of requirements? How do we ensure that we can utilize some of the digital tools that are available today to start tracking things like our, energy and power supporting infrastructure early in the weapon system development process? It's something that should be very doable, but you can imagine it's not done today because those are disparate communities. So I think, at the beginning of the day, Mo mentioned some of the challenges that AB InBev has when it comes to some of the logistics, the supply chain management. We have those exact same challenges in the Air Force, right? And a lot of the same digital tools give us the opportunity to break down those stovepipes and really, work to facilitate that process early in that acquisition life cycle, right? So that's kind of the mundane example of saying, hey, just at an MBSC perspective, there are some opportunities to really deploy and plan for our advanced energy technologies in conjunction with our system development. Then we also have kind of the more flashy examples, right? So over on the operational energy side, we've done quite a few projects where we do, say, 3D scans of aircraft. Those are incorporated into, full digital models. I won't get into kind of the differences between digital twins and digital models, but we do have some of that information available. And those tools really permit us to go through and expedite the deployment of some of our, drag reduction technologies, our energy saving technologies. By having those models available, it facilitates all of those future projects that we do. So it's not just, a one-off every single time we go through the same, PDF-driven, approval processes. We can leverage these models. We can expedite the deployment and get these capabilities to the field faster.
Awesome. Yeah, and I think, that's a perfect example, I think, and refers back to one of the themes that Daniel really drew out, which is that, these digital tools, digital engineering tools and models are really ultimately about supporting people who are implementing the work. And I think that's a great opportunity to bring in Ben Masters. Ben is the senior research physicist at the U.S. Army's Engineer Research and Development Center at the U.S. Army Corps of Engineers. Ben, you're working on some really exciting and fascinating work on the possibility of mobile nuclear reactors. And that's a good reminder to everybody that the work and missions of the Department of Defense carry some unique challenges and risks. And so one of the things that I'm curious about is, how might you think about applying digital engineering tools to mitigate some of those risks on what are, essentially no-fail missions with, challenges and consequences associated with them? How could digital engineering help accelerate, the development of a workforce and the training and compliance requirements that are obviously associated with your work?
Mike, thanks first for having me. That's really like 5 questions in one, so I'll try and answer them sort of in sequence. So you mentioned the importance of no-fail missions, and those really start with training and being prepared. I see digital engineering as being one of the solutions in training future soldiers, whether it's on existing assets like fossil fuel generators, the methane 10 or technically quiet generator, or in the future, should we get a mobile nuclear power plant, training them on that. The nice thing about digital engineering is that a couple of things is that it's not nearly as resource expensive as running the actual generator or reactor. And second, you can undergo scenarios or do things with it that would not be advisable for an actual physical asset. I'll just put it that way without going into specifics. And you can also anticipate maintenance. So one of the things that that the Secretary of the Army earlier this year talked about in their 6 objectives to help guide the force is ensuring that the Army becomes more data centric. So if we can leverage digital engineering and virtualization of actual assets, whether that's at installations as a whole, or at in operational energy, looking at power production, being able to first measure all of that, analyze it, and then predict, just sort of moving along the evolution that Chris alluded to early on in this conference, being able to anticipate the kind of maintenance that's going to be needed before it happens, and then actually test out that maintenance ahead of time without having to take your system down. That's a big deal. And also, I should mention, the Army Corps of Engineers has the responsibility for civil works as well. And we are largely responsible for things like locks and dams and bridges. And you can imagine when a lock or dam is down, that's potentially billions of dollars of commerce that doesn't go through in a given day. If we can anticipate things, even as seemingly trivial, it's not trivial, but even as seemingly trivial as corrosion, just by using the information that we can collect from digital twins on a big lock or dam, that could save an enormous amount of time. And I'll just quickly go back to installation energy. In addition to training, just being able to monitor the effect of N+1. What happens if we bring one more building online? What happens if we do one small change? What happens if we if we convert from this type of lighting to another type of lighting? Being able to use all of the data that could be brought in through digital engineering, as well as anything that can be derived from virtualization, that can save an inordinate amount of energy in and of itself. So Chris and I have been working on a way of doing that specifically for training, and without stealing Chris's thunder, I think it could be a major game changer.
Absolutely. I mean, I think, when we talk about energy systems and infrastructure investments, we're talking about huge capital outlays that are, meant to last decades, and a process both within DoD and in the rest of the country that's in many ways outmoded from, a permitting standpoint and things like that, in ways in which those kinds of investments must be accelerated. And I think your question is essentially, how can digital engineering play a huge role in accelerating the deployment of solutions? And I think that's also a good opportunity to bring in Nick Rinaldi. Major Nick Rinaldi is the Human Performance Portfolio Lead at the Army Applications Lab. Nick, your job is to help accelerate and transform the Army's interaction with industry and the private sector and outside stakeholders, and it seems to me like a lot of that in support of the Army's modernization priorities. And it seems to me a lot of what Ben and Daniel have mentioned really hopefully strikes a chord on how you might be sort of accelerating the deployment of that transformation. So I guess my question to you is, could you give a little bit of a background on the Army Applications Laboratory's collaboration model? How do you work with these outside stakeholders? And then how might digital engineering already be implicated and applied within some of the solutions you're offering and working on? But also, how might it also be expanded and grown within your portfolio?
Yeah, no, thanks, Mike. I appreciate it. And thanks for having me on. I think the Army Applications Lab is actually a really small organization that doesn't have like large amounts of funding. So where you see kind of our greatest impacts is probably like examples of how you could approach something from a stakeholder build standpoint, or from a solution sourcing standpoint. And predominantly from the innovation space, we manifest that through technology acceleration, usually through commercial dual use products. So we're probably not building a tank or like a large nuclear, infrastructure scenario for us, but we might be involved in some of a larger project that helps like make that thing better, faster, stronger. And we run the gamut on things that we'll go after for the Army and the modernization priorities for Army Futures Command. Anything from energy to robotics, AI, human performance, kind of you name it. We have a category called emerging opportunities. So you know what that means. It's kind of the rest of whatever doesn't fall in those categories. And we really, the way we approach some of those things is through, the sourcing of problems from the warfighter, and then bringing those problems back to then search, folks that we don't already work with to solve those problems. And I think in the past, we've been predominantly in a small business paradigm for that, but with our additional kind of RDT&E funding, we kind of break that out to anyone that could solve a problem, bringing them to the table to help do that. But different maybe than some of the other innovation offices you may have seen or attempts at project work in experimentation. We really try to bring to your question, Mike, we try to bring our stakeholders to the table to solve those problems. So what I mean by stakeholders is when we look at a problem that, say, someone in the Army has, usually an operational unit, we will surround that problem owner with our requirements writers over in Futures Concept Centers. We'll surround them with other S&T folks that are partners internal to our adjacent units, such as development commands, labs, and centers. We'll reach out to others that are adjacent to Army Futures Command to help us solve a problem. We'll work with kind of any of the Army commands, any of the DoD, agencies, labs, and centers that would have equities. And then we'll reach out to those PEOs, those acquisition professionals that are going to end up catching the thing we solve, because that's usually the problem is whatever the problem is, no one can catch it and sustain it. And so we really want to bring those people in early. And so, after about 20, 30 good stakeholders are around that problem and that problem owner, it's kind of when we end up launching a project to solve. And we'll bring in commercial vendors to solve those problems, usually competition-based acquisition. And that's not a unique thing at all, but just the way we do it, I think is helpful. Maybe not the only one that does that, but definitely helpful on how we approach and solve those problems. I think digital twins and modeling, which I by no means am an expert in, some of those examples that we've seen, I think what I've seen from manifestation wise is the actual implementation of that at a warfighter level. So, we've seen, augmented reality or modeling for training our soldiers in maintenance on various platforms. At this point, they could be all of the platforms. That's one of the projects that we've worked a bit here. And then also kind of where I see it, I have got a human performance background, and so where we're working in social lethality is predominantly in the biomechanics of the modeling piece of that. And then, how do you apply specific equipment that we're looking to add to the soldier or change, the environmental conditions or the types of slope and grade that they're going to be walking across, just to really exercise digitally that piece of equipment or technology that we want to apply to the human. I think there were some great comments on the panels earlier, and then in this one as well, about how do we become more data centric? How do we use the modeling appropriately so that we've got several iterations that get to like a good and best product before we go to build. Those are definitely applications that we want to leverage. I think and we could honestly leverage better if our data sets were not as disparate as they are. I think, at least from an Army standpoint, and I think we're making good strides towards that. A lot of the policy that's been coming down from the DoD has been extremely helpful, and some of the reorganization that's occurring there from a data standpoint. So excited about that. And a lot of the thoughts that Eric kind of brought up earlier about breaking down the barriers between services on a cross-cutting technology specifically. I know he's talking about energy in particular, and we had that interaction a little bit earlier this year about doing some of that. You see it in other areas that just everyone's got humans, and so you see that exact same kind of methodology apply here with digital twin modeling, and then breaking down those barriers ahead of time virtually versus having to build something physically for people to realize that this should be like an all servers type of event. So I think there's some great pieces there. I'll pause. Thanks, Mike.
No, Nick, that's great. I mean, I think the one thing that, and maybe this is just an opportunity for you to plug, but like, if people want to learn a little bit more about some of the things that you're doing, and I can attest, as Nick alluded to the power of this collaboration model, where they are building like communities of practice and communities of stakeholders. They held a terrific event in Austin around energy challenges, and combining a lot of the traditional program managers with a lot of private sector innovators. So where can they learn more, I guess, about what you're doing?
No, thanks. I appreciate the pitch there. So AAL.Army is our website specifically. We launch our projects there. You can ask a question there, and there's people on the other end that respond, I promise. And then we have the Vertex series that Mike mentioned in April of this year. I thought was a great way to begin some collaborative efforts. There were connections made there that not only like business to government, but business to business, that were super valuable moving forward, and understanding like how the Army could approach something, being informed by industry and in the commercial sector. Folks like Ben from ERDIC were there. And participated in that, and so not just AFC and not just Army Futures Command was there, but in the kind of circus of organizations underneath that. But there was all kinds of folks that participated in that, and it was a small event meant to be intimate to promote discussion. We're doing another one in December 7th and 8th for it's the focus is on human performance for that event, and then we've been asked to hold a recurring energy Vertex series probably in April or May, and once those details are out, Mike, I'm going to make sure I get them to you and to folks that are interested. But it's not about just like talking about the problem, it's or the problems, right, whatever those are. It's about building those communities that can help us actually collaborate and think about a problem differently, so that we can build those approaches into our government requirements, which ends up driving that whole bureaucracy train that you've mentioned before. But there are folks that are change agents in there to make that happen, and I think those type of events can really help inform us and then and take action, which I think is kind of some of like the predominance of the part we got to do.
Absolutely, yeah. And speaking of problem solving, change agents, and like government and business interaction, I think that's a good opportunity to bring in Andrew Heiger, who's the Deputy Director of the Advanced Energy Portfolio at Defense Innovation Unit. Andrew, like your entire organization and like ethos is built around sort of warfighter problem solving, and doing it more rapidly and than before, and in particular leveraging commercial solutions to do that. So I guess, and also to just take a step back, Andrew, you also have a background on from the combatant commands, your time at combatant commands, on like problem solving sourcing, and so problem sourcing and requirements generation. So I just wonder if you could share a little bit about DIU's approach to some of these problems, and then Daniel mentioned already interacting with DIU around some of those challenges, but just share a little bit about the model and ways in which digital engineering can help accelerate some of that solution providing.
Yeah, thanks, Mike, and thanks for having me and having DIU here to represent some of this. And as you said, DIU really is set up, designed to deliver this, these transformative capabilities to the warfighter faster than what was done before. I'm not a digital engineering SME by any means, but I do really believe that there is a place for this, not just in the lab, but in actually getting the best tech into the hands of our warfighter in the field, right? So taking this out beyond the lab environment. I think we're starting see that more and more. I'll back up for a second and just talk about the combatant command point that you brought up, because that is my background. I've been working with the combatant commands for years now. I sat at Southern Command for almost 5 years, and the combatant command provides a unique perspective. So I'll touch on that before I get into DIU, and DIU's partnered quite a bit with the combatant command, so it's applicable anyway. So the combatant commands, they're there to solve operational problems, real world problems, and so they really are the demand signal for what technology is needed to bridge these gaps. Right? What technology needs to get out in the field and needs to get out in the field in the very near term to solve real world problems. So very much focused not on S&T for the sake of S&T, not that there's anything wrong with that, but a very different focus, and it's actually a focus that DIU shares. Our projects tend to be on the 1 to 2 year timeline. We have a very strict definition of transition, so we really are talking about fielded technologies. So a lot of this aligns with the combatant commands. It's actually why I was brought into DIU originally, was to partner with the combatant commands. But the combatant commands also have a unique problem that they face, which is that typically they don't have the funding to solve the problems that they need to solve. So it's a nexus of the technology needed to solve the problem, the funding needed to do the development to solve the problem, and then what is that actual requirement or problem, and putting all three of those together. And DIU really comes and sort of sits right in the middle of that problem. While we're not a funding organization, we kind of create the partnerships both within DoD and the private sector. So we sort of sit in the right place to do that. Now the question is, where does this digital engineering all fit in to do this? And I think Daniel made a great point that you're starting to see this in DoD. This is not new. In fact, while I was at Southcom, we were the first to do some physics-based modeling to determine how best to deploy ISR assets. So this is a great example. I mean, if you think about what it would have taken to do trial and error on these very expensive, very exquisite assets, flying all over the Eastern Pacific, it's a real world thing that you're solving here with digital engineering. You're saving money, you're saving time, you're potentially keeping the warfighter out of harm's way, right? So we did this physics-based modeling to determine, okay, this is where the assets should be deployed, this is how they should be deployed, what does the coverage look like of each asset that has different types of sensors. So it was quite a comprehensive model. Now that was a little bit of a one-off because I was very interested in how we can employ digital engineering to do this. But I think you're starting to see it more and more. I think the combatant commands can use it to solve real world problems. But I also think this is kind of where DIU comes in. So I think what you're seeing here, and I think what's exciting is the advancements both in the private sector and in DoD, right? So Daniel talked about what DoD is doing. We stood up a whole office in R&E, which, by the way, DIU sits under. We are within that same organization. So you're seeing DoD put a stronger emphasis on this, which is fantastic. But you're also seeing the other side of the house, and we saw it earlier with the examples of Budweiser and things like that, where the private sector has the acceleration of the technology in the private sector. Just in my time as an engineer, from engineering school to now, which might be longer than you might think, but there's been a huge acceleration in that technology. So DoD has the emphasis, which is fantastic. You're starting to see all the panelists here see the value, right? The DoD is starting to see the value. The private sector is, as is the case with a lot of things these days, really leading the way. And then you've got DIU sort of sitting right in the middle. We are set up to leverage those advancements in the private sector. We do this through our commercial solutions opening. We do this through our OT authorities to do rapid contracting. We have commercial engagement teams engaging with the private sector across all fields where the the private sector is matching with the OSD modernization priority areas. That's why we have 6 portfolios. And within those 6 portfolios, I'll talk now a little bit about, I think, where energy is and what we could be doing, are doing, and what could be doing with digital engineering. So you heard some of the other panelists already talk about kind of the 2 main focus areas of energy, and this is true for our portfolio, and that's installation energy and operational energy. So Ben hit on some of this, but with those, that's not unique to DIU, right? So we put our focus in energy on those 2 areas. There's a number of reasons why that I don't have time to go into, but you could probably all guess on that. But I think the digital engineering world can sort of help with both of these areas, and again, a lot of that's already been hit. But I think what we need to do is really be able to leverage the private sector better. You're seeing rapid growth, rapid acceleration in the private sector on this as it pertains specifically to energy. Better sensor to modeling, closing the gap between what the sensors are seeing and what the modeling is doing. That's happening at rates that we haven't seen before, which then leads into the prediction, so predictive maintenance, which was touched on. But even before that, and some things we're doing here in the energy sector of DIU, we're even doing some of the before deploying, doing some of this digital engineering to make sure that we can meet all the metrics we need to meet without having to do it. And you heard some of the other panelists touch on sometimes deploying can be very high risk, high cost. So one project where we're using digital engineering is a project to put energy storage in the Arctic, right? So -60, difficult environment for energy storage, but we're looking at it in advance in a sort of a digital engineering way, so that we don't have to go drop a battery energy storage system, right, to a place where really nobody wants to go, and the system could break, and you've wasted a lot of money in doing that. So that's one example. But I guess I'm just overall excited to see the progress in the field. I think we could be doing more with it. That example is a perfect one of how the private sector is doing that. We're doing it in advance of deployment, and it shows where we're looking to deploy in austere or difficult environments. How digital engineering can help. So a lot of stuff there I went over, but yeah, I'll pause there.
And Andrew, just to round us out, if folks want to learn more about some of these opportunities, it's diu.mil, correct?
Yep, and like Nicholas said, we do reply. So DIU is a pretty small organization. If somebody sends a request through our website, we all see it. Somebody will reply, and I would encourage everybody to reach out. We really are looking to partner with the private sector, with DoD. Some of the panelists here, I think we need to get in touch, right? We all need to be talking. So I would say not just private sector labs, even some of my DoD folks on the line here, please, let's reach out and sort of connect on some of this stuff. I'd be happy to.
And Andrew, that's a great pitch, I think, for the kind of work that we're hoping to do at the in-person event that Chris will be leading in Idaho in April, that he mentioned before. Before I round us out, because I know we're short on time, I feel like I gave the opportunity for Nick and Andrew to make some pitches for things if you want to learn more. Daniel, Eric, Ben, anywhere that you want to pitch just for if folks want to learn more about your organization and the work you're doing?
Yeah, so I'll jump in really quickly and give 2. So from the energy perspective, please, you can reach out directly to me. For those who are kind of looking for maybe a little larger overview of all the great work going on in the Air Force when it comes to digital transformation, really easy website. It is dafdto.com. So dafdto.com. That's really where we have started to compile a lot of the great work going on the Air Force side.
Perfect. Thanks, Eric. Daniel?
You can find kind of a lot of our stuff on the Chief Technology CTO.mil website. It's best just to Google it. Admittedly, our branding on that site is a little hard right now. We're working on a public open digital engineering body of knowledge website. So once that's out, obviously want to get more people involved with that. But right now, you guys just Google digital engineering DoD and you'll find our website on CTO.mil.
Perfect. That's what I did. So yeah. And anything, I know your work is a little bit different in nature. So anything though that you'd want people to keep up with publicly?
So I could just say a couple of things. Anything regarding what I touched on earlier for training, talk to Chris. He's definitely the expert on that. And I, like most other folks here, I am not a digital engineering SME. But I will say that ERDIC does have some digital engineering assets here. It's actually at our sister lab. So I'm at the Construction Engineering Research Lab in Champaign. The Information Technology Lab down in Vicksburg, Mississippi is the one that primarily handles digital engineering, although I think there's some going on at almost every lab at this point. So if anyone has any questions, either please let me know and I can probably link you up with the right person, or you can go to www.erdic.usace.army.mil, and there's a lot of different fact sheets out there with points of contact in case you were looking for something more specific.
Awesome. Well, gentlemen, this has been a great conversation. I'm sorry we don't have more time, but really appreciate all your time and your insights about this critical topic. So back to you, Chris.
Thank you so much, Mike, and our DoD panelists for all your time. We have a couple more exciting digital engineering technologies to show you from the national laboratories. First, on dice.inl.gov, there's a registration link to today's 3 p.m. Eastern vendor presentation from ANSYS and Oak Ridge. Second, we have an excellent video from Sandia National Laboratories, who's really a key partner in realizing this digital engineering future. So Eric is going to play Sandia's digital engineering video right now.
System design is currently undergoing a profound makeover. Digital engineering is allowing engineers to utilize software that is integrated, interconnected, and interactive to improve efficiencies and shorten timelines. For example, in the automotive industry, digital design has reduced the time from concept to manufacturing a new car model from 6 to 8 years down to 18 months. Airplane engines are completely sensorized, providing a digital twin, and we can render the internals of any system virtually. Now you might ask, how could this paradigm shift change how the weapons complex could define, design, and engineer nuclear weapons systems? It currently takes many years to build a nuclear weapons system. Congress and the NNSA are asking how to shorten schedules and cut costs in order to reduce waste and be more responsive to future threats. It's time to unsilo the process. To be more responsive, we are implementing a digital engineering ecosystem throughout the nuclear security enterprise that will completely modernize how we develop systems. Imagine all the necessary modeling software and authoritative repositories seamlessly integrating. We understand that engineers will need to dramatically change how they do their jobs. They will require new tools, training, collaboration, and there will be enforced compliance. But the result could be up to 75% reduction in cost and schedules with a significant improvement in quality. Simply stated, the future of a successful nuclear deterrence is implementing a fully automated digital engineering ecosystem. We must continue to further our engineering skills by creating unique tools and techniques to advance system design. Our engineering capabilities must adapt to anticipate national security threats. The future is now.
This video is intended to walk you through what model-based systems engineering is and how it is being used here at Sandia. Today we will highlight how we are applying MBSE and what we are doing that is unique to the nuclear deterrence mission. There are 4 core elements to Sandia's MBSE approach as illustrated by the gear diagram. We have found that by establishing these architectures, requirements, functional, physical, and verification and validation, we're able to cover the systems engineering operations needed to realize a system from start to finish. Each architecture is complex on its own, but together they enable us to better understand the associations and dependencies across all areas of the development lifecycle. This ultimately helps us manage the data, understand it, communicate it, and then leverage it to make informed decisions.
Hello, I'm David Ferguson, a systems engineer at Sandia National Laboratories, and today I'm going to give you an accelerated overview of our Test for Knowledge project. With T4K, we have a vision of one team, one tester, one target, resulting in a trusted tester capability that ensures mission delivery without delay. We have a focused mission of developing a capability for holistic model-based design, coupled with a unified data strategy infrastructure. The current state of testers is reactive, lacks a unified approach across the lifecycle, does not leverage modeling and simulation to the extent it should, and as a result, testers are always on the critical path for first production unit. Today, product realization teams mature their product designs to the point of inflexibility, typically moving into final design phase before fully considering their tester needs, and without input from the experts on testers. To address these issues, we are building 3 core capabilities into the T4K framework: digital engineering, to utilize and implement value-added paradigms to the tester development and realization process, including model-based systems engineering, model-based design, and model-based realization. Interoperability, to develop integrated workflows that allow for the flexible utilization of multiple toolsets to seamlessly transfer and communicate data, and credibility, to identify standards to assess our modeling, simulation, and analytical workflows. Over the past 2 years, we have executed multiple pilot projects to prototype tools, processes, data, and products, which will culminate in a T4K demonstrator project in FY23 to showcase application of the T4K framework for a wider audience. Finally, we are also relying on parallel increases in our MBSE and MBD capabilities. For MBSE, we have a new assessment tool called the MBSE Maturity Matrix, which refines the broader NSE model-based enterprise maturity matrix. Thank you for your time. Hope you have a great day.
All right, welcome back. So that is a video from our partners at Sandia National Laboratories. So Anthony Mata, if he wants to come up on the screen for a second here, he's a senior R&D manager. We introduced him earlier. So if you have any questions about Sandia's digital engineering technologies, just reach out directly to Anthony. Or if you don't know Anthony's email, you can reach out to me and we'll get you connected. So I would again like to thank our thrilling panelists from across the federal enterprise. These were some of the great beginning conversations for how to bring digital engineering technologies to our federal assets. And I'm pleased to announce a save the date for the first multinational laboratory in-person digital engineering conference on April 25th and 26th here in Idaho Falls. We hope to see everyone there. Have a great afternoon, everyone.